It gives me immense pleasure to introduce you all to our next session. And as promised, this is the much awaited session. So, all you guys who have stick throughout the day, I hope you guys have enjoyed all the sessions that were planned for you, all the people that came in from different walks of life, from different parts of the world. And now we have one more speaker, a surprise entry for all you guys. Although I'm sure you already know about this and you guys have been waiting for this. So let me quickly introduce you to our next speaker, our chief guest for the symposium, someone who is also an IEEE fellow, professor of computer science at ETH Zurich, none other than Professor Onur Mutlu. His broad research interests are in computer architecture, system hardware security, and bioinformatics. Professor Onur has also received several prestigious awards, including IEEE High Performance Computer Architecture Test of the Time and IEEE Computer Society Edward J. McCluskey Technical Achievement Award. And of course, it's our absolute true honor to listen to his thoughts on the intelligent architecture for intelligent systems.
Okay, great. Should I get started?
Over to you, absolutely.
Okay, excellent then. Okay, thanks for inviting me to give a talk in this conference. Unfortunately, I missed a lot of the conference because it was night during my time frame, but hopefully you will enjoy this talk. So I'm going to talk about intelligent architectures for intelligent machines, which is along the lines of the topic of this conference quite a bit. We're going to mainly talk about memory and storage, essentially data. And I think I have 45 minutes, so if I go over, please let me know, because I have material to talk about for days and days. But we're going to talk about computing.
Just try. So the time limit for today is 30 minutes, 25 minutes for the speaker session, and we are trying to keep 5 minutes for the audience questions, because I'm sure audience will have tons of questions after this session.
Okay, sounds good.
Yeah.
So I will start then. So we're going to talk about intelligent architectures for intelligent machines, and the problem is that today's computing systems are very much limited by data, bottlenecked by data. And data is key for many applications, AI, ML, genomics. Important workloads are all data intensive. They require rapid and efficient processing of large amounts of data, and data is increasing on top of this. We can generate much more data than we can process. And data is key for many workloads. These are some workloads that we're used to. They're going to become even more data intensive. It becomes a performance and energy bottleneck. These are some mobile end workloads, less server workloads, but they're equally and maybe more so data intensive. In fact, we're exercising some of these workloads right now as we do remote calls. And data is performance and energy bottleneck in these workloads. And some future workloads are going to be even more data intensive. This is genome analysis. Today, we can sequence genomes much faster than we can analyze them. We have many potential analyses that we can do on genomes. And this is becoming much more powerful because genome sequencing devices are becoming much more powerful. You can see that they're becoming less costly. And this is clearly very important, especially as we are seeing with the COVID-19 outbreak. But there are many applications in terms of health and scientific discovery of life, etc. Basically, today, we're bottlenecked by the data that we can produce. We're unable to analyze it efficiently and at high performance. And I'm not going to talk about this in detail, but this is clearly an important application. And we do some work in this area, understanding how we can make genomics much more efficient and much higher performance. And today we have devices that look like this, that can fit into your hand. You can buy with relatively low cost compared to other devices in the past. And you can sequence a lot of things, but then processing of the data and analysis becomes a huge bottleneck because this device is not able to process data locally. So you have to send the data that you produce all the way to data centers somewhere. And it takes a long time to process the data because I don't think we have good principles to actually operate on the data where it resides today. And this is just one example of a potential future platform we can build if we can actually rethink how we design the computing systems so that we make data less of a bottleneck than today. So if you're interested in genome analysis, we have written a lot of articles on it, and this is a more recent survey article that we wrote at IEEE Micro. I would invite you to take a look at it. And we also write papers where we actually do specialized designs, hardware, software, co-designs that can accelerate genome sequence analysis, in this case, approximate string matching, which is at the core of genome sequence analysis. So in the future, I think this problem is going to be even more important for many reasons, health reasons, medical reasons, as well as scientific reasons. And we're going to have more edge devices like this, and we will need to have much more efficient methods of computing on this data. And if you're interested more in this, we have lectures about also. Sorry, I hear an echo. Is there a question or? Okay, I hope it's not on my end. But we give lectures, so you can take a look at the lectures if you're interested in these. And these slides will be available if there's a I'm happy to send it to the conference organizers, but I also put them on my website. Okay, so hopefully this gives you an example of many applications requiring a lot of data. And data, in the end, overwhelms modern machines. It overwhelms the storage and memory capability, communication capability, and computation capability. It greatly impacts robustness, energy, performance, and cost. And when you look at a computing systems from a first principles perspective, we have fundamentally three key components: computation, communication, and storage. And we have heavily optimized the computing unit. Everything else is there just serving the computing unit, moving and storing data. And as a result, we have systems that are overwhelmingly imbalanced. We have systems that look like this. This is my cartoonish picture, of course, but if you look at any die photo today, most of the system is really dedicated to elements that move and store data: caches, interconnects, other caches, other interconnects, memory controllers, other caches, other interconnects, shared memory, interconnects, storage. So more than 90%, 95% of the entire system of a single node is designed to move and store data and not compute. So we call these computing devices, but they're really not computing most of the time. They're most of the resources dedicated to moving and storing data. So we'll come back to this. We'll try to fix this problem. This is there because we have a processor-centric design paradigm in our systems today. Okay, so as a result, we have data coming up as a performance energy bottleneck and overwhelming our machines. And this is one example we will get back to, but we did the study with Google a few years ago where we found out that more than 60% of the total system energy is spent on data movement on important applications that I showed you in this particular slide, including machine learning, web browsing, video playback, and capture. Okay, so I will start with this axiom, basically. I will say we want to design intelligent architectures for the future because these architectures, these platforms are going to make decisions for us going into the future. And they have to be intelligent. And I believe that intelligent architecture has to handle data well. I'm not going to question this from now on. And of course, the question becomes now, how do you handle data well, right? And I'm going to give you three different directions that are complementary to each other. And I believe they should be done together. But we're going to focus on one particular direction for the purpose of this talk, since we don't have a long amount of time. But basically, we need to ensure that data does not overwhelm the components that we design via intelligent algorithms, via intelligent architectures, and via intelligent whole system designs, algorithms, architectures, devices, all together. I'm going to especially focus on this part. We also want to take advantage of vast amounts of data and metadata flowing through the system to improve our decisions over time. So a good system learns from past behavior. And I believe as humans, we are learning. We have a lot more to learn, of course. We can do better. But if you look at the systems we design, computing systems, they don't really learn, at least at the very core of them, hardware, for example. For example, we design the memory controllers and storage controllers. They don't really adapt their decisions to the workloads over time based on what they've learned. They don't change their scheduling policy, power management policy, etc. So we need to have more intelligent systems that take advantage of data, more data-driven architectures. I'm not going to talk about this as much. I'm going to briefly mention in the next slide as well, but I'll direct you to some lectures that you can watch if you're interested. And the third perspective is we want to understand, exploit properties of different data so that we can customize our algorithms and architectures to different types of data and different properties of data. Some data is very important for security, for example. Some data is not very important for security. Some data is very important for error tolerance. Some data is not that important. If we can somehow distinguish these different types of data, we can make much better decisions and optimize our systems much better. So architectures today, based on these three directions, are not doing well, basically. They're not doing well, dealing well with the data because they're processor-centric as opposed to data-centric. They're mainly moving and storing data, and very little amount of time and real estate is spent on computation. We're going to focus on this a lot in this talk. They're also not good at taking advantage of vast amounts of data and metadata available to them over time. My cell phone, for example, is still using the same algorithm it is using to schedule memory operations, for example, and it hasn't learned anything over the course of 6 years as it has seen workloads. It hasn't customized itself to me or the workloads. And I think this is a big problem with an intelligent architecture. So that's why I don't consider existing architectures intelligent, because they make human-driven decisions as opposed to data-driven decisions. They don't learn from their mistakes. And the third is our architectures today are not do not know or exploit different properties of application data because they're designed to treat all data the same because the characteristics do not get communicated well from the higher levels, from the semantic levels to the hardware in the system. As a result, architectures make component-aware decisions as opposed to data-aware decisions. They cannot adapt the decisions to the properties of the data. Again, I'm not going to talk about data-driven and data-aware aspects of architecture design much in this talk, but they're as important, if not more important than data-centric. I believe they're all together very important, but we're going to focus on data-centric purely because of time reasons. Okay, so let's jump into data-centric or memory-centric architectures. I also call this as processing data where it makes sense. Essentially, if you think about data-centric architectures, there should be multiple properties. We're going to focus especially on the first one, processing data where it resides, where it makes sense, as opposed to moving data far away from the processing units into the processing units that are far away. But we also want low latency and low energy data access, low cost data storage and processing, and intelligent data management. I'll touch upon intelligent data management a little bit to motivate processing data where it resides. Okay, let's jump into it. I call it processing data where it makes sense. The basic idea is data is stored in data storage units, whatever they are, tape, SSDs, hard disks, memory, caches. We're moving data to accelerators and processors that are far away from them today. Can we actually do better? Can we actually process data where it resides, where it's generated, where it's stored? And this is not a new idea. This is an old idea, actually. Early incarnations of it go back to in-memory processing, like logic and memory computer that I show you over here. It's as early as 1960s. But today may be the time where we really actually take this idea finally serious and make it commercial and change the paradigm of computing in all of our systems going into the future. Why is today the time? I think we have a huge problem with technology today because memory technologies that we have designed are having a lot of problems, and maybe we can make use of them in a better ways. I'm going to talk about that to motivate a little bit. And we're looking at controllers close to DRAM, and industry is finally open to new memory architectures today. I'm going to mention that later on also. So we have a huge push from technology, but we have a huge pull from applications and systems as well. So let me talk about the technology push today. Basically, today we're looking at interesting systems that look like this, 3D stacked memories, for example, where you have logic underneath memory, where you can do logic very close to memory at high bandwidth and low latency. And there are other examples that I will show you later on where people are trying to incorporate processing elements inside the DRAM chips. And they have actually done it. They're commercial products that you can buy. But why is this motivated? What is this motivated by? Basically, we are motivated by memory scaling issues. We're having trouble with technology scaling. And this is a paper that we wrote a while ago. If you're interested, you can take a look at it. But basically, memory is having a lot of issues. And one issue is reliability. This is data that we collected with Facebook over the course of 1.5 years. We analyzed all of the memory areas in Facebook's data centers, and we found out that memory reliability is reducing, and memory reliability is causing system reliability problems. Essentially, the chips that are denser have more errors. As a result, servers are failing more than before because they're employing these chips that are less reliable. Why are they less reliable? Because cells are closer to each other. They're more vulnerable to many different types of noise. Cells are smaller in storage, in memory. And as a result, we're having trouble with reliability. Okay, if you're interested, you can read more about it. We're not the only ones writing about it. There are also other works you can find. We also built infrastructures that look like this to understand such issues at a really fine-grained level. These are FPGA-based infrastructures where you can put memory chips and test the memory chips for different types of errors and different types of issues. I'm going to talk about what we have found. We have found a lot of things, but I'm going to pick and choose some examples. But if you're interested in actually doing studies with real memory chips, we actually open source this infrastructure, and you can actually relatively easily do studies on real memory chips using an FPGA-based infrastructure like this, and we'd be happy to help in this direction. So while we were doing a lot of studies together with Intel using this infrastructure, we found out that one can predictably induce memory errors in most DRAM memory chips. This is now known as the DRAM RowHammer problem. Essentially, you can predictably induce bit flips in most DRAM memory chips that are out in the field. And this is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And people are writing articles that sound like this. At the core of it, forget software. Now hackers are exploiting physics. I like this title over here because it has a nice higher level reflection of what RowHammer is. So RowHammer is basically what I'm going to show you here. All memory is composed of rows, and you can activate the row to read data by applying high voltage to a word line in memory. This is DRAM. And this is called opening the row. Now, if you do this repeatedly, activate high voltage and then pre-charge, low voltage in the DRAM, activate pre-charge, activate pre-charge, activate pre-charge, activate pre-charge, high voltage, low voltage, high voltage, low voltage. It turns out adjacent cells that have nothing to do with the part of memory that you're activated, except being physically adjacent, get corrupt, meaning they flip from 1 to 0 or 0 to 1, depending on different circumstances we analyze in the paper. But this should not happen, basically. We're just reading this part of memory. We're not even reading potentially, we're just activating and pre-charging. And we're affecting data that is stored in some totally unrelated addresses. And these addresses could belong to some other processes. These addresses can belong to the system, the operating system. As a result, this poses not a reliability problem, but a security problem. So we call this the hammer row and victim rows. And we showed that this problem exists in more than 80% of the memory chips that you can buy out in the field today. Whereas it should not happen, because this is a serious reliability and security problem, as I will show you a little bit more as well. So this was not happening in chips that were manufactured before 2010 because cells were not close enough to each other. This happens because cells are too close to each other, and the activation that you do on one cell is affecting the data that's stored in other cells because of multiple reasons. Certainly electromagnetic coupling is one reason. And cells became too close to each other in recent technologies. As a result, all chips that we tested that were manufactured between 2012 and 2013 are vulnerable to these errors, independent of the manufacturer. And this is a reliability and security problem because it breaks memory isolation, which is really a key property, key pillar of a reliable and secure computing system. And we said when we wrote the paper, an access to one memory address should not have unintended side effects on data stored in other addresses. And I still strongly believe in this. And we said in the paper that someone can hijack your computer exploiting this. And later, folks from Google Project Zero showed this. And there are a lot of interesting security works that came about later that show that you could do it in remote systems by exploiting RowHammer in a remote server, for example. You could do this in Android phones, but intelligently. An Android phone, an application you download can actually hammer your memory and take over your system, get access to all kinds of private data, etc. And more recently, people have shown that RowHammer bit flips cause problems in deep neural networks. Essentially, they showed that you could reduce the accuracy of these deep neural networks from 90%, for example, all the way to something like 10%. Essentially, these deep neural networks become useless. If you're employing them in situations where your life is dependent on these deep neural networks, or some other people's lives are dependent on, for example, in self-driving cars, or in some medical predictions that you do using neural networks, you may actually get completely bad outcomes. So that's why this is a serious reliability, security, and safety problem. And if you're interested, you can read more about it clearly. And we have written multiple papers. I'm going to flash some of these over here. But to solve this problem, we need intelligent controls. Essentially, we want controllers. You want intelligent memory that doesn't have these problems and that prevents these problems, scaling problems, before they actually get exposed to the user. So this problem has not gone away. I wish that it was gone away. Unfortunately, the problem is not fixed yet. In 2020, we have analyzed RowHammer again, and we found out that newer DRAM chips are actually more vulnerable to RowHammer because of technology scaling, and existing mitigation mechanisms are unfortunately not effective. So we need to actually look at new ways of dealing with this. And we also showed that existing DRAM chips that are claimed to be RowHammer free are actually not RowHammer free, because some intelligent attacker can reverse engineer the DRAM chips just enough so that they can actually cause these bit flips that were the problem to begin with. So we're back to square one, and we need to fix this problem going into the future. And I think people who may be listening to this talk may be interested in some potential solutions. And we would, of course, welcome many solutions. And this is one solution we developed. This is one of the most recent solutions that was published in HPCA. I'm not going to talk about it, but it involves an intelligent memory controller to identify hammering patterns and to ensure that those hammering patterns do not cause bit flips. And if you're more interested in RowHammer, I would recommend taking a look at some of the lectures that we deliver as well. Okay, so this is one example of a technology scaling problem that causes serious safety, reliability, and security issue. I liken this to a bit flip that happens in critical infrastructure like bridges, right? Bridges are clearly critical infrastructures. Humanity has been designing bridges for thousands of years, and we know that they're critical. We try to make them robust, etc. But sometimes there are bit flips in critical infrastructure. So computing is much more critical today. Computing is going to be used in essentially everywhere in our lives, like making life-critical decisions, medical decisions, self-driving decisions, self-optimizing decisions. And if it goes wrong, its implications are going to be much worse than bridges like this. And bridges, unfortunately, these bridge accidents also happen. This is in Korea in 1994. This is in Minneapolis in 2007. This is more Genoa more recently in 2018. Now, I think in computing, we're more lucky than bridges because bridges are very heavy infrastructure. In computing, we have more patchability, essentially. So, okay, I talk about this in my undergraduate lectures also, saying that this rod is very strong, but if you get a bit flip in it, these people may not be very happy. So I think we need to take security more seriously going into the future, security, safety, and reliability. We need to think about preventing unforeseen consequences because we're going to trust our lives on these computing platforms, like this example of a self-driving car with Mr. Bean, for example. Okay, so a big challenge of an opportunity for future going forward is designing fundamentally secure, reliable, and safe computing architectures. And I think this requires predicting and preventing such safety and security issues like RowHammer, but RowHammer is just one example of it. There are other issues that I'm not going to go into, like retention errors, but other errors in storage and memory are also going to be serious. But to be able to fix these, I believe we need intelligent memories, intelligent memory controllers, in-field patchability, programmability, so that the memory controller can intelligently detect that this sort of attack or this sort of reliability issue may be happening, and it fixes the problem without exposing anything to the user. Okay, so this was a push from technology part. We want intelligence in the memory system. But there's a huge pull from systems and applications today that didn't exist even 10 years ago or even 5 years ago as well. I'm going to talk about that. It was always important, but it's becoming much more important. Essentially, data access is an increasingly major bottleneck today. Energy consumption is a key limiter, and data movement energy dominates compute. We're going to take a look at each of these quickly, and then we're going to take a look at some solution directions. In my opinion, the key question is this. Going into the future, do we want sustainability and energy efficiency in the world, or do we want a world that looks like this, that's going to be terrible for our children? I think we want energy efficient, sustainability, but we also want high performance to solve the problems. The question is, how do we get there? And I think before we answer the question, we need to identify the problem. I think the problem is data access today is a huge performance energy bottleneck at the very core of the design of our computing systems, because our current design principles cause great energy waste. They also at the same time cause great performance loss. I put this in parentheses because even though they cause great performance loss because we move data all around, we try to avoid that performance loss by designing the system and making the system more sophisticated, more complicated in hardware and software. Unfortunately, that causes even more energy waste. So we're in this vicious cycle today. Data access, we know, is a major bottleneck. It causes energy problems. It causes performance problems. To avoid the performance problems, we're causing even more energy waste and even more complexity. And I think we need to break this vicious cycle. To break the vicious cycle, we need to process data far closer to the data and identify the problem as processor and memory dichotomy, basically. We want to get rid of the processor and memory dichotomy. Essentially, a computing system consists of computation, communication, and storage. We want to merge them together, if you will, because today's computing systems are very processor-centric. As a result, we have all these problems, as I mentioned, and I'm going to mention also. Basically, because of the processor-centric design paradigm, memory becomes a huge bottleneck. This is Dick Seitz. He was the chief architect of Alpha computers in the 1990s, which were the fastest of their time. And basically, they designed the flagship Alpha processor in 1990s. And he basically wrote a one-page article in Microprocessor Report titled, "It's the Memory Stupid." And basically, he analyzed the performance of this Alpha processor. He said, basically, we designed this processor over the course of, let's say, a decade. And we optimized it so that it can finish 4 instructions every cycle, but it's finishing 1 instruction every 5 cycles, let's say. So it's operating at 5% of its peak bandwidth. Why? It's waiting for data to come back from memory. And he basically said that he expects over the coming decade, memory subsystem design will be the only important design issue for microprocessors. And I think we need to keep that perspective going into the future. This is data from my own PhD thesis. We found essentially something very similar together with Intel. We found out that most of the time, the processor is waiting for data to come back from main memory. And if you're interested, you can look at our analysis in this paper. And this is data from Google. Google found out essentially the same thing more recently. Most of the time, the processor is waiting for data to come back from memory in their system because we have a processor-centric system. Okay, so essentially, because we have a processor-centric system, the system is grossly imbalanced, and it's energy inefficient, low performance, and complex, and the processor becomes complex and bloated. This makes things even more energy efficient, low performance, and complex. And as a result, we're back to the picture that I showed you earlier. We call this a computing system, but it's most of the time, most of the resources are dedicated to moving and storing data. Now let's look at the energy perspective quickly. So this is data from Bill Daly. I borrowed this slide. This is relatively old, but it's essentially things have not changed as much, even though the absolute values have changed. This is a complex arithmetic operation, 20 picojoules energy. this is a memory access, 16 nanojoules energy. So it's 800x difference. So a memory access consumes 2 to 3 orders of magnitude the energy of a complex addition. Make that a simple addition. Even a simple addition is like that today, actually, because this was data from 2012 or so, if you will. So basically today, in order to operate on data, we need to do an operation that's 2 to 3 orders of magnitude more costly than the operation itself. Now the question becomes, does it really make sense to move the data over these energy-hungry interconnects to do a simple energy simple operation? And because we don't do that today, more than 60% of the total system energy is spent on data movement. As a result, our systems suffer. So I will posit that we do not want to move data. We want to design data-centric architectures, and we want to change the paradigm shift to enable computation with minimal data movement, compute where it makes sense, where data resides, and make computing architectures more data-centric. So what does that mean? Essentially, we want to enable processing wherever data resides, wherever data is produced, as opposed to having to process the data in the processor and the accelerators. So memory is a special example of this. I'm going to talk a little bit more about memory in this case, but our principles apply to storage. Our principles apply to wherever data is generated. Sensors, for example, in an IoT system, you may want to do processing inside the sensor, processing inside the camera, processing inside the screen, for example, as well. Okay, but let's focus on memory, because memory is a place where a lot of data is stored in conventional computing systems, and we can store our applications. Basically, we would like to be able to ask memory, can you execute this function on this database for me? And the memory responds with results. So there are many, many questions over here. I'm not going to answer all of them clearly in this talk, but how do you design the memory and the controllers? How do you design the processor chip and in-memory units? How do you design the software and hardware interfaces? The system software compilers and languages, and the algorithms and theoretical foundations of computing. So this is really an across-the-stack problem, all the way from algorithms to devices. It even threatens or maybe questions the theoretical foundations of computing, because if you have taken a theory of computer science course, and many people here on this course may have, you're counting operations, right? The complexity theory is based on counting how many operations you do using an algorithm. But maybe that's not important. Maybe how many memory accesses is much more important from an energy perspective and performance perspective. So in a data-centric architecture, you really need to question the very fundamentals of the compute-centric theory, processor-centric theory that we have developed over the course of 5, 6, 7 decades. Okay, let me quickly give you examples of what kind of benefits we can get with different approaches to processing in memory, and then we're going to conclude. So I'm going to give you 2 examples. One is processing using memory, and the other is processing near memory. So these are both examples of processing inside memory, let's say, processing in memory. But processing using memory takes advantage of the analog operational principles of the internals of the memory cells, so that you can do computation without adding a lot of logic. So it's minimal approach, let's say, by changing the memory to do computation slightly. But those operational principles already exist. Processing near memory is adding extra logic closer to memory. Okay, let's take a look at the first one, processing using memory, with some example. I'm going to start simple. I'm going to talk about data copy and initialization. We do a lot of data copying and initialization in our systems today. And Google has found out that a significant fraction of the cycles in their data centers spent on data copy and initialization, as you can see, just 2 functions actually. But how do you do data copy today? How do we copy a page to another page in memory today? Basically, we have to go through the processor, because we are processor-centric. At least the memory controller we have to go through the DMA engine. So this is high latency, this is high bandwidth, cache pollution exists, and unwanted data movement, because you may not actually you need the data that you're copying immediately. So this is expensive for a small page copy, 4 kilobyte page copy via direct memory access. It's about 1,000 nanoseconds and 3.6 microjoules. Now, if you show this picture to a child and maybe ask the question, does it really make sense to move the data all the way into the processor whenever I want to copy a page to another page inside the memory? Maybe you will get the simple answer saying that, oh, why don't you do this inside the memory? Because it's much faster that way, and you're not moving data unnecessarily to somewhere else where you don't need it. And that's the idea, basically, in memory copy. It's low latency because we're going to exploit the internal bandwidth. It's low bandwidth utilization because we're not going to move the data on the very expensive data movement part of the system. No cache pollution. I'm not going to talk about that, but you can eliminate that today with DMA. No unwanted data movement, essentially. And I'm going to show you a mechanism very quickly at the high level that takes us 1,000 nanoseconds to 90 nanoseconds, more than an order of magnitude improvement, and 3.6 microjoules to 0.04 microjoules. And the idea is very simple. At the core of it, in DRAM, analog operational principles enable you to do this. In fact, you can do this in real DRAM chips without changing the DRAM interface today, as we have shown and as others have shown before us as well. So basically, the idea is, in order to copy a row to another row in DRAM, you first activate the source row, which brings data into the sense amplifier strongly. And then you activate the destination row, which takes the data from the sense amplifiers to the destination row. Essentially, by using the sense amplifiers as a buffer, you can do the data copying very quickly inside the DRAM itself. So the idea is 2 consecutive activates, negligible hardware cost. In fact, existing DRAM chips can do it if you modify the memory controller today. And that gives us more than an order of magnitude latency reduction, 74x energy reduction on the memory side. And you can do this, actually, we have generalized this mechanism. I'm not going to talk about the details, but you can actually get similar results wherever the data resides inside the DRAM chip. And if you're interested, you can take a look at these papers that I mentioned over here. You can do faster copies. You can do small granularities, interbank. I'm going to talk about computation next, but these are the papers that you may want to also take a look at if you want to look at the optimizations that are more recent. But we're thinking about memory as an accelerator now. We want to add specialized computation capability inside the memory, and the memory can actually do this computation very efficiently without disturbing the processor. And it's very similar to a conventional accelerator, except it's much more efficient because it doesn't have the memory bottleneck. Okay, so similarly, we can do in-memory computation. We can do in-memory bitwise operations, majority and or not. I'm not going to go into the details of how we do it, but we essentially exploit analog computation capability of DRAM. Activating multiple rows performs computation, and this leads to between 30 to 60x performance energy improvement in each operation. And you can take a look at this paper if you're interested again. And non-volatile memory technologies that are emerging enable even more opportunities. People have shown this as well. You can, for example, do matrix vector multiplication using analog current mixing. And you can also do similar operations like what we proposed, row clone, as well as bot bitwise operations in these technologies as well. But these technologies have an advantage because they're non-volatile, so you can operate on data with minimal movement. Okay, I'm going to give this idea very quickly. If you have triple row of activation, it gives you a bitwise majority function due to the chart sharing, analog chart sharing principles of the DRAM circuit. So the final state is bitwise majority, which is a great function on top of which you can implement actually real applications. I'm going to briefly mention a paper that we wrote recently on this. But you can also have and or functionality by setting C to 1 or 0. And then you can also add not functionality by taking the data, complement of the data from the other side of the sense amplifier to the array. And we talk about all of this in our paper. If you actually take advantage of those bitwise operations, you can accelerate database queries significantly end to end. And this is from our paper. We show that you can accelerate some important database queries by 4 to 12x, and your performance scales with the size of your data, which is a nice property, as long as you can fit it inside the DRAM chip, of course. Okay, if you're interested in more, there's a lot more information on this that we have written. I'd recommend you take a look at it. This is the most recent work where we showed that you can actually do even more complicated operations, and you can do it as a framework using majority and not functions. I'm not going to talk about it. You can also do interesting security functions inside DRAM, physical unclonable functions and random number generation, for example, by taking advantage of the analog properties of the DRAM chips. Again, I don't have time to go over it. But let me quickly go over the other aspect, processing near memory, even faster than what I have done with processing using memory, so that we don't delay things further. Processing near memory is very interesting because now you can add general purpose computation logic arbitrarily close to memory, basically. Of course, there's a cost equation that you need to consider, but you can have it in the memory controllers, you can have it in the 3D stacked logic layer, you can have it inside the DRAM chip. But the question is why? Why do you want to do this? Because you want to accelerate important applications and make them much more efficient. And one important application we studied was graph processing. Clearly, graphs are everywhere. They're in machine learning, they're in bioinformatics, they're in social networks, they're in representing large amounts of data. And scalable large-scale graph processing, graph analytics is very challenging. As you can see, if you throw cores at it, you don't get benefit because you have frequent random memory access and little amount of computation. So the question we asked was, can we actually take advantage of 3D stacked memories for this? Add logic inside the logic layer in 3D stacked memories, where memory and logic are tightly integrated using high bandwidth, low latency, through silicon via connections. This technology is becoming even better today. We're going to have monolithic 3D architectures going into the future, which is an extension of this, in my opinion. And we designed the system that looks like this. Essentially a distributed system that takes a 3D stacked memory and combines it with many other 3D stacked memories so that you can have a scalable system. But internally inside the 3D stacked memory, you can see that we have in-order cores, and these in-order cores are connected via an interconnect, and you can actually do message passing communication between these in-order cores, and you can partition your graph across the memory, and you can actually operate on the partition graph by sending messages between the in-order cores. So we don't move the data here, we move the computation to the data by sending messages. Again, I'm not going to go into the details of this. There's a lot more detail because it's a full system design. I'm going to give you some results. But this is essentially a distributed in-memory processing system. Communications are done via remote function calls to the in-order cores that house the data. And we have sophisticated prefetching mechanisms that I'm not going to talk about. But the system looks very different from a conventional system. These are conventional systems that we compared to. There's a processor and memory dichotomy. So you can easily say, these are the processors, these are the memory. Here you cannot tell. Here basically every single component is processor and memory at the same time. Processing is done, tightly integrated with the memory, and you combine the components. As a result, very high amounts of bandwidth is available to the processors that we design. And the performance benefits are significant, as you can see. These are averaged across 5 important graph processing algorithms. We get about 13 to 14x performance improvement. Now, LaterWorks, this is work from 2015, as you can see. LaterWorks improved our design. They actually came up with very nice ideas. And the performance improvement currently is about 2 orders of magnitude, more than 100x, based on the initial design that I mentioned. And the energy efficiency is also similarly good. It's basically more than 8x. And again, recent work has improved this because we're not moving data out of the memory chip as much as possible. We're getting significant energy efficiencies. Okay, if you're interested, there's a lot more on this. I will very briefly mention that you don't have to change the entire system to get some benefit from processing in memory. In this work that I alluded to earlier that we did with Google, we actually analyzed consumer devices, and we basically looked at these important workloads to understand the bottlenecks. And I gave you already this data point. We found out that more than 60% of the data, total system energy in these workloads is spent on data movement in mobile devices. And we wanted to actually do processing close to memory using 3D stacked memories as similar to what I mentioned earlier. But we wanted to be more realistic. We basically said, we want to offload functions. And then the question becomes, which functions do we offload? And it turns out a significant fraction of the data movement often comes from very simple functions that are in your programs. And we analyze those simple functions, and we design simple low-power cores to execute them near memory, and simple fixed function accelerators as well. Of course, fixed function accelerators are more efficient because they're customized for those functions. In my opinion, having reconfigurable logic near memory is going to be even better. So I think we want to have heterogeneous execution units near memory, cores, accelerators, and reconfigurable logic going into the future. And we showed that you can actually gain, by being careful about what you offload, you can actually gain by more than 2x performance and energy improvement in real workloads like the ones that I mentioned. So just to give you an example, these are the workloads. And machine learning inference, for example, TensorFlow Mobile is Google's machine learning framework. Machine learning inference is very much bottlenecked by data movement. More than 50% of the inference energy spent on data movement. And more than 50% of that data movement energy comes from packing, unpacking, and quantization operations. I'm not going to go into details of what these are. Again, I'm happy to answer questions, or you can watch other lectures. But these are very simple functions to manipulate data that goes into your neural network, or that goes into the next stage of your neural network. And by offloading these operations to main memory, you can significantly accelerate and make energy efficient the machine learning inference. Okay, so if you're interested, there's more in this paper. And clearly, there are other papers that I'm not going to talk about. But I'm going to give you a very quick overview. You can do distributed GPU processing using processing near memory. And there are papers that are about it, which we don't have time. You can accelerate linked data structures, which are at the core of many interesting data traversal algorithms today. And I think this is important going into the future. You can accelerate dependent cache misses, accelerate prefetching mechanisms. You can accelerate important applications like climate modeling. I will briefly mention this again. And approximate string matching, genome analysis, time series analysis that are employed in many scientific applications like astronomy, for example. And you can get significant energy and performance in all of these things that you can accelerate near data by reading these papers. You can find out exact numbers. But usually it's more than an order of magnitude compared to existing systems. But to be able to do all of this, I think we need to revisit the entire stack, because this is really algorithm, architecture, device, and logic co-design in the end. But I believe we can get there step by step. I'm not going to exactly talk about how we get there step by step. We need to look at simple things like row clone that I mentioned, simple changes to the system so that we can get benefits little by little. Of course, it's important benefit in some applications, but maybe over time, these benefits will accumulate. That's what I mean by step by step. And if you're really interested, we have written overview papers. This is a more recent overview paper that talks about processing in memory. And this is an older overview paper that talks about workload and programming issues. But the good news is these systems exist now. We were writing, and other people were writing actually papers about it earlier in the recent incarnation of processing in memory, let's say early 2010s. But now there's a company, UpMem, that has actually produced these chips. They call the DRAM processing units. They have a processor near each DRAM bank, and we actually work with them. These are the memory modules. These are real systems that we ran. And if you're interested, you can learn more about the processor that they have designed inside the DRAM bank. This is a talk that my senior researcher Juan delivered recently. You can take a look at it. And this is a paper that we have recently released on experimental analysis of the Upman PIM engine. And it turns out there are some workloads where this system is much stronger compared to state-of-the-art GPUs and CPUs. And you can take a look at the paper. We've also released benchmarks, so you can actually do your own benchmarking of the system once you get access to it. I think FPGA-based processing near memory is also important. We've been dealing with 3D stacked memories that are connected to FPGAs, and we see significant benefits for genomics, for example, and weather climate modeling as well. And this is a very recent paper that we just completed that you may want to take a look at if you're interested. And these are real data from real systems, both of these works. And more recently, Samsung announced that they are actually finally developing processing in memory systems. As you can see, this is as early as as late as February 2021. And they basically call what they're doing function in memory, which is essentially a near memory processing engine, where the near memory processing engine is really customized for, let's say, what they call AI, but what I would call matrix multiplication, as you can see. So basically, they have near each bank, they have computation units that can do efficient matrix multiplication. Okay, I'm not going to go over this in detail, but this is good news in my opinion. Finally, the industry is actually moving towards these architectures, maybe little by little, but that's good. You change the paradigm, hopefully over time. And if you're interested, we have detailed lectures on PIM, and a much more longer version of this talk is available as an IEDM tutorial, but it doesn't have some of the newer insights that I showed you clearly because of the difference in the date. Okay, so basically, I think I'm almost done. We want fundamentally energy efficient architectures. That means that the architecture needs to be data-centric. We want fundamentally high-performance energy computing architectures. That means that the architecture needs to be data-centric again. So data-centric architectures provide us with energy efficiency, high performance, and I believe more sustainability going into the future. I also believe more reliability and security and better scaling. So being data-centric, being memory-centric actually comes up with a lot of benefits and eliminates a lot of the problems that we face in today's computing platforms. And hopefully they enable computing architectures with a minimal data moment. Of course, there are adoption issues, which we did not discuss. I'm not going to discuss them. Clearly, we need to solve the adoption issues like functionality, applications, software. A lot of these adoption issues are related to software and programming, but there are hardware issues as well over here and the hardware-software interface issues. We try to tackle some of these issues. I don't have time to go over them. Coherence and virtual memory, for example, runtime systems, compilation systems, security, and infrastructures. But I believe all can be solved with a change of mindset. And the change of mindset is essentially shifting our mindset from the processor-centric paradigm to the data-centric paradigm. Okay, again, I think we can get there step by step, but eventually we will need to revisit the entire stack. And if you're interested, we have also released another paper on arXiv that provides a new methodology for understanding data moment bottlenecks and a workload suite, and you can take a look at it. The workloads are also released as open source. And I believe if we do all of this, we can enable new medical platforms, health platforms, new platforms in general. Medical is interesting to me because we have been working on bioinformatics and genomics. And again, I think there's a lot of potential here. And if you're interested, you can take a look at these works. So what we do not definitely have time for is the two other aspects of opportunities for the future. We want data-driven, self-optimizing, self-learning, self-growing architectures, self-evolving architectures, if you will. I'm not going to talk about that, unfortunately. We also want data-aware, more expressive computing architectures where the semantic information about data and computation is communicated to the underlying architecture of the system so that we can have a much more efficient system. And I believe this data-driven and data-aware go along very well with data-centric because these are really three things that, in my opinion, should enhance all of the architectures. They have good synergies with each other. And again, more info is in this tutorial as well as backup slides. The backup slides have some slides on data-centric and data-driven architectures. So now let me conclude. Hopefully, I've given you examples of how we're not dealing with data today, and data is our major bottleneck. Today's architectures are processor-centric as opposed to data-centric. They're human-driven as opposed to data-driven, and they make component-aware decisions as opposed to data-aware decisions. I think it's time to design principal system architectures to solve the data problem, which is our major problem today. We want to design complete systems to be truly balanced, high performance, and energy efficient. And hopefully that will lead us to intelligent architectures. And I think intelligence comes from at least three principles: data-centric, data-driven, and data-aware. In my opinion, actually, we see all of these three principles in nature as well as the way we humans evolve. I don't suggest that we know everything about humans and nature, of course, but there are some principles that are that we know that are along these lines that make us maybe more efficient and maybe more intelligent than actually our counterparts in machines. We would like to enable computation capability inside and close to memory. And I believe, hopefully, I've convinced you that this can enable orders of magnitude improvements and new application and computing platforms, maybe better understanding of nature because we would be perhaps closer to nature, maybe better than it in some ways, and who knows what else. So I think we do need to go towards data-centric, data-driven, data-aware architectures. And maybe we can find better principles for architecture system designs. I don't claim to know all of the principles again, but I think a distributed system like what we have in the brain is not a processor-centric system. And I believe many people have shown evidence for it, scientific evidence for it. And I believe we need to discover other principles clearly going into the future. But to be able to do that, we really need to think step by step. And most importantly, we need to have open minds. I believe we need to exploit good principles, some of which we know. I've actually talked about a lot of these principles in this talk without naming them necessarily. Some of them I named, I think. But I think more importantly, we need to have open minds such that we can change, do the paradigm shift. We cannot, whenever we think processor-centric, we should be able to say, this is a remnant of the processor-centric paradigm. Maybe if we think differently in a data-centric way or data-driven way, a data-aware way, we can solve the problem in a much better, much more fundamental way. And we don't have to waste a lot of energy and performance on this process-centric remnant of our thinking. Okay, I will briefly mention the papers that I would recommend and the talks if you're interested. I will acknowledge folks who have supported our research. Thank you, and please keep supporting us. And I will most importantly acknowledge my group who has enabled all this research, as well as collaborators, of course. You can find the list online. And this is my group pre-pandemic. This is my group during the pandemic. Well, during the pandemic is here, actually. If you're interested, you can actually take a look at our newsletters and learn more about the people who have been who have done this work, as well as people who are doing other work that I didn't get a chance to talk about. And all of our reference papers, talks, and artifact software is available online on these websites you can find. Thank you very much. I appreciate your patience, and I'm happy to take any questions at this point.
Absolutely. Thank you so much, Onur. It was indeed a high-intensity knowledge-sharing session for all of us, and it was worth the wait. We were actually looking forward to the session, and what a wonderful session, I must say. Having said that, since you just mentioned about the pandemic situation, how's the situation out there for you guys?
Could you say it again? Oh, the pandemic situation.
Yeah,
oh, okay.
For you, yeah.
It's getting better. Of course, things are opening up a bit warily, but we'll see. Of course, it's a bit unpredictable, clearly in all of the world.
Yeah.
I hope things are better. I hope things are better in India.
Yes. It's still, again, I think we are facing the same thing, and I think we're sailing in the same boat. So let's just hope that better days are ahead of us.
Yeah, I agree.
But thanks to the virtual world that we are able to connect today. That's the beauty of science and technology.
Yeah, that was I think the benefit. I didn't have to travel because travel is much harder. But this is
absolutely, and I think it's an honor to have you here with us today. So now let's open the room for audience questions because we have received multiple questions for your session. So now I would request Ankit to come in and please put forward the audience questions now.
Sure. Thanks, Minnie. Guten Morgen, Professor. Marhaba.
Marhaba, Ankit.
So I have multiple questions lined up and what a talk. So it's always a privilege listening to you.
Thank you.
I will have to make a selection of which questions to ask. So yeah, going by chronological order across your talk, I have questions like the eraser correction, ECC, basically in memory. Can it help slow down the hammer attack that you mentioned about? Can we have some correction codes built in so that we can fight it out?
Yeah, so that's a very good question. In a longer talk, of course, we discuss all of these issues related to RowHammer. But certainly ECC can help because it can correct some of these errors and it can detect some of these errors. But the ECC is not enough, basically, today, because the existing ECC mechanisms that are employed either inside DRAM chips or in the memory controller can detect one error and maybe can detect two errors and can correct one error. because they're too costly to build otherwise. And we have found that with RowHammer, you can induce more than 4 errors in an ECC code word, essentially. So you need to have a much stronger error correcting code than what we have today to be able to get rid of all of the RowHammer problems. And I think I would argue that that's not an efficient solution to RowHammer, because ECC error correcting codes are great to deal with errors whose causes we do not know of. Meaning, usually if you have a random bit flip, for example, retention errors tend to be this way, or soft errors tend to be this way. If you have a random bit flip, it's very hard to solve that problem without something else other than ECC, error correcting code. But RowHammer, we know exactly why it happens. We know that somebody is accessing this row or particular rows very, very heavily. And we can design a leaner mechanism, lower cost mechanism than strong ECC that can actually fix this problem. So in my opinion, ECC, if you make it strong enough, yes, absolutely, it will fix RowHammer. But the strength of the ECC that's required to fix RowHammer would be, in my opinion, prohibitively expensive, because I believe we have better methods for fixing RowHammer.
Sure, sure. So next question, actually taking along on those lines, if we actually build a model, a deep neural network based on the access that you're seeing, like if RowHammer is active at some point in time, you're seeing a different pattern than usual. So can we actually predict that there is an upcoming issue that's going to happen?
So that's a good question, actually. That's something we have not looked into. And maybe that's something worthy of investigation. Somehow, I'm not sure if deep neural network is the answer, but some sort of a learning mechanism, let's say, that can detect anomalous access patterns, right? I think that's what the question is getting to. Right. Potentially, yes, potentially. So right now, what's happening is in the solutions that we have developed and some others have developed, we're trying to figure out these anomalous access patterns that are intensive access patterns using not learning mechanisms, but more like Bloom filters, for example, by keeping track of how many accesses you have done to a particular row in an approximate manner, but in a manner that's good enough to actually detect the problem. Learning can potentially be employed here. I don't know. I think it's a good area of investigation. I cannot say it's a better or worse direction. It depends probably on the learning mechanism. But I would recommend the person who's asked the question or anybody who's interested to potentially take a look at what machine learning can bring to solve this problem. In the end, I think the solution needs to be adoptable widely. The solution needs to be low cost. So I would recommend trying to make the solution low cost, whatever learning-based solution it may be.
Sure, sure. So actually getting along from the slides that you presented, so much of the RowHammer attack is, or as you have investigated, is in case of the DRAMs, right? So is some of the newer technologies like the persistent memory, for example, let's say Intel Optane, also susceptible to something similar?
So that's also a good question. Basically, the high level answer is yes. But there's a caveat in the sense that, so for example, there was a paper in ICCD a few years ago that showed that STT-MRAM is susceptible to RowHammer. There are papers that show that phase change memories are susceptible to similar disturbance phenomenon, like write disturb phenomenon. So I'm not sure if the disturbance is exactly the same as what we see in DRAM, for example. Hard disks are, for example, are susceptible to write disturb phenomena also. So there's certainly disturbance, hammering phenomena in general, whether it's due to writes or reads. It depends on the technology. But in my opinion, as you scale the technology down to smaller sizes, this electromagnetic coupling happens in all technologies in some way. And people have shown that this does happen in emerging technologies as well. Now, I don't know if particularly Optane is vulnerable to this, because clearly there's a controller that protects Optane, right? Intel doesn't release Optane as raw chips that you can hammer, as far as I know. There's an internal controller that does error correction. There's sophisticated error correction, as far as I could tell, in Optane chips. So they may be correcting some of these errors internally as well. Or their technology size may not be small enough to observe some of these disturbance effects. Because even in DRAM, finally we are getting into technologies where RowHammer is a huge problem. Right. So in my opinion, the short answer is yes, but the other technologies currently have controllers, intelligent controllers that are trying to fix the problem, whereas DRAM is not having those controllers.
Sure. I guess because you would also need an FTL equivalent thing for Optane, because it suffers from wear leveling. The life of the entire transistors is probably not going to be like DRAM. Like you can store and read as many times as you want, practically, but then Optane has a life. So I'm guessing like that might also be instrumental in protecting it.
Yeah, absolutely,
So,
absolutely. Actually, we have done a lot of work on flash memory SSDs, and we saw RowHammer-like effects, read disturb effects in flash memory, much worse than DRAM. But the FTL, flash memory controllers, can fix the problem easily because they do a lot of other things anyway.
Right,
Yeah.
right. So, a segue from what you just mentioned. So, from your work in the flash area, so do you also have some recommendations or things like in-memory operations for persistent memories or non-volatile memories?
So, I mean, we are looking into it more so than before right now. But yes, I think certainly it makes sense to look at in-memory operations for flash memories as well as other types of memory. And I think, again, the principles that I mentioned apply for both of them, processing using memory as well as processing near memory. For example, in flash memory or phase change memory or some sort of memristors, you can do analog operations internally, bulk bitwise operations similar to what I mentioned. You could do row clone type of operations. You could also do matrix multiplication like many other works have shown. They built prototypes actually for this. And I think that's a very good direction. But there's also another direction, which is adding computation elements next to the memory. Flash memory controllers are actually very good examples of this. In the storage SSDs today, you have ARM processors, you have FTL, and you can add a lot more logic inside there, or you can execute programs inside there. And we have actually been looking into that as well. So I think the answer is, again, yes. And again, I think the processing in memory types are applicable to all types of memories. And in my opinion, we should explore all of them to find out the different types of trade-offs we have with different types of memories. Because in the end, in my opinion, different types of memories will be part of the solution of the future. And ideally, we would like to be able to do the processing in all of them. We don't want to move the data again all the way to the processors and accelerators that are far away from the memories.
Sure, thank you. And next question is more like a trend-like thing, because we deal with storage, and what we have seen is, like in storage systems, we have tried to scale up all the way till HCI, where you are putting in the compute and the storage together. But then people are also moving towards disaggregated storage and disaggregated architecture. And you're saying because that the compute and the storage and everything doesn't scale the same for all applications. Do you see that in future when we start having chips, like you mentioned about UpMem, they are building and processing into the chips and memory chips. So it would be like a PIM, not a DIM, as an it sits on the memory bus. And but then at some point in time, you would also want, I want more compute, I want more storage, and then different combinations. And then you will ask for a disaggregated architecture around that. So do you see that as a trend coming in?
Yeah, I think there's, in my opinion, that's a good trend also. In my opinion, there's no single silver bullet, let's say. If you want to really scale the system, like have hundreds of terabytes of memory, today we don't have the technology to put that in a single node, right? And I believe disaggregated memory is certainly a good trend. In fact, we have some work on it also. That was one of it was just published in this ASPLOS. I believe disaggregated memory is a good trend for applications that require those huge amounts of memories. Of course, I don't think that the disaggregated memory goes against processing near data. Whenever you have disaggregated memory, for example, you can offload computation to that memory server that stores huge amounts of memory as well, right? In my opinion, whenever we build disaggregated memories, we should also try to move the data as little as possible. If we can ship the computation to the remote memory, for example, we can again avoid the data movement. But today, I think what we're doing in the design of disaggregated memory systems is we have this node, and we're actually moving the data into the node so that we can process it. And the memory server is not doing computation. Of course, I think with RDMA, things change a little bit, right? Things have changed a little bit. But I think we need to push a little bit further so that we can scale up the system and have a lot of memory by disaggregating it, but we can still localize the computation to the data without moving the data. I don't know. Hopefully that makes sense.
Sure. And there were like so many things that we would want to continue listening to you about. I guess in a subsequent edition of our conference, we would want to have you again as a speaker, because I think there was a lot of content you had to trim because of the limited time. So I will save some of the questions due to lack of time at the moment. And thank you so much for joining us remotely.